organized as mentors and mentees. It was a great experience and really fun to me. The first speaker in this session is Eren from Bilkent University. Initially, we intended to study the philosophy of mathematical foundations, but after he learned type theory and fascinated by the charm of the proof assistant, we changed our target. Today, he will talk about type theory and a proof assistant named Agda. Enjoy your talk.
Okay. Hello, everyone. Before starting, I would like to thank the organizers of this amazing event for giving us this opportunity. And I also want to thank my mentor, Elif, to introduce me this interesting area of mathematics. Unfortunately, today I was not able to attend in person, but I think I can make it up for the next time. Okay, we can start now. What is type theory and why should we care about it? So firstly, what is type theory? There are lots of type theories, but we will mainly focus on Pier Martin-Löf Type Theory. In type theory, every object comes within a type. We write it in that syntax. An element of type is called term in type theory. We use two dots here. And we cannot talk about elements in isolation in type theory. We have to specify what is the term's type. Like, let's give us some examples here. 0 is a term of type natural numbers, and true is a term of type Boolean, and f is a term of functions from natural numbers to natural numbers. So let us give a formal definition. Type theory is a formal language, a set of rules for writing certain strings of symbols, which describes the introduction of types and their terms and combinations with them in a meaningful way. I highlighted meaningful because it's also a philosophical choice. What do you mean by meaningful and what do you consider as true? But today we will not dive into that discussion much. Okay. An important aspect of type theory is we can implement our logic inside type theory. That is not the case in set theory. In set theory, you have to use logic to deal with sets and their elements. But in type theory, within the system's rules, we can implement our logic. And today, we will see these definitions and some examples of that later in the presentation. So why type theory? I discussed the differences between type theory and set theory a little bit here. It's because it's an alternative foundation for mathematics. And in set theory, why can we choose type theory as a foundation? Because in set theory, we are forced to use sets. And this has some strange side effects, like in von Neumann's construction of natural numbers, 1 is a subset of 2. And when you want to define a function, what is a function? It's not natural to define it as a special kind of relation or as a set. The natural way to define a function for me is it's like a black box, which takes an input and produces an output. And type theory helps us hide these strange side effects. Let us talk about a practical problem, proof checking. When we talk about mathematics, we generally consider it as a most certain science or language, whatever you prefer here. But mathematicians who do mathematics are only human. And we see lots of examples of mistakes in either proof writing or proof checking. Because of that, we want computers to handle this problem because computers generally do not make mistakes. And that possibility is observed by two mathematicians, Curry and Howard. And this approach is called Curry-Howard isomorphism. It states that we can see propositions as types, and a term of a type, a proposition, can be considered as a proof of that type. This approach can help us extract computer proofs from human proofs. Let us give a quick example here. Let's say we want to prove this classical theorem of logic called modus ponens. We write it here like that, and we are looking for a term of it. If we manage to find a well-typed expression here to be equal to this proof of modus ponens, it means by Curry-Howard isomorphism that we have found a term of this type, and it means this proposition has a proof. Okay, we will do it, the proof, actual proof, at the end of the presentation. Now let's talk about Agda. It's a proof assistant, which is built on a programming language called Haskell. It helps you write proofs, as we will see the details later. Unfortunately, there was a technical problem today. Because of that, I will not be able to make an interactive proof, but I will give all the details, so I hope it will not cause any problem for understandability. Let's see how do we define natural numbers in type theory. We first say write data to indicate to Agda that we are declaring a new type. And it's a term of set. Set is a reserved for word used for set of all mathematical objects in Agda. It's just a naming. We declared it here, and we give the constructors of natural numbers, like in Peano's classical construction. 0 is a term of natural numbers, and successor is a function from natural numbers to natural numbers. If we want to define what is 1, first we have to say that 1 is a term of type natural numbers, and then define what it is. 1 is defined as a successor of 0, and so on. And usual arithmetic operations can be defined like that, as Peano did. So how can we produce other types from given types? In set theory, when we have two sets A and B, we can talk about their intersection. A intersection B is a new set given to sets A and B. And one line later, we can talk about the properties of its elements. Like in intersection, X must be both in A and B. Similarly, we have 4 rules to create a new type in type theory. These are, firstly, formation rule. It states how to form a new type. Second, introduction rule, how to construct elements of the type. And thirdly, elimination, or sometimes called induction rule, how to use elements of the type. And lastly, computation rule, how the elimination rule acts on introduction rule. Let's give an example to these 4 rules. Let's see a specific type in type theory, product type. Record is a similar word for like data. Given two sets A and B, we can talk about their like Cartesian product in set theory, A times B. Its elements are given in the form A comma B. It's an ordered pair like A comma B. And the first one belongs to A and second one belongs to B. And this implementation is hidden here under the field environment. The formation rule here is A times B is a set. Introduction rule is given by constructor, comma. And elimination or induction rule says that if I want to write a function from A times B to another type C, then all I have to do is to define f A comma B. And why do we call it also induction? As you see here, if I want to define a function over natural numbers, then all I have to do is to deal with base case, 0 and the successor function. And all other elements are hiddenly implemented here with these 2 lines. It's because of that sometimes called induction rule. And computation rule says that if I give A comma B to projection 1 function, then it gives me back A. And similarly, projection 2 function gives me back B. I have also a coproduct type, sometimes called disjoint sum. A term of A disjoint sum B comes exactly from 1, A or B. And these 2 functions exactly say that an element of A union B is comes from B or A. So this is different from our classical union. And why have we defined these 2 types? Because we will be using them while we define our logical conjunction, as we will see 2 minutes later. Okay, I have a unit type. As the name suggests, it has exactly 1 element. Let's call it TT. Since it is automatically non-empty, we will be using it to define true in logic. And I have also an empty type. which, as you see here, there is no introduction rule, no elements. And we will be using it to define falsity in logic. So here comes the logic part. From now on, I will be using the name prop instead of set, just for convenience. Let's define our first conjunction, and. Okay. And if it takes two arguments, P and Q, and produces P and Q, and it's defined as P times Q. Why is that? An element of P times Q is given as an ordered pair, P comma Q. And by definition, P is a term of uppercase P and Q is a term of uppercase Q. Curry-Howard isomorphism tells that if P is a term of uppercase P, then P is a true proposition. And similarly, Q is a true proposition. We also define logical conjunction or as disjoint sums of two sets, P disjoint sum Q. And if P or Q is true, then either P or Q is true. And in our Curry-Howard isomorphism point of view, it has a term P or Q has a term Q, lowercase q. Okay, these are well-behaved conjunctions. Curry and Howard showed that. Now comes a little bit strange definition. P implies Q is defined as a function from P to Q. Since we are we are in the perspective of Curry-Howard, we can interpret it as a function which takes a term of P or a proof of P and transforms it to a proof of Q. So if I have a function which transforms from proof of P to proof of Q, and I have P, then it means I have Q, and which is called modus ponens, which we will prove at the end. Okay, as I said, I define true as a unit type. It's by definition non-empty, hence automatically true, and false as an empty type. It is automatically empty, hence false. And negation, also definition of negation is a little bit strange. Negation is defined as a P implies false. So if I have not P, and at the same time if I have P, that means I have a function from P to false. That means there is a term of false, but by definition it is impossible. So P cannot be true. We can interpret it like that. The if and only if is defined classically with an and conjunction. And here comes the most important part of the presentation. We will prove modus ponens, and we will do it without truth tables. In classical lectures, we always do it with truth tables. If P is true or Q is true, and like that. For a small proposition like modus ponens, it's not a big problem. But when you have a composite proposition like De Morgan, it gets messy really quick. So this approach is somehow a time-consuming one, less time-consuming. So first, I write my proposition as a type, and I am looking for a term of it. Let's call it MP. I write question mark here. Since Agda is a proof assistant, it should help me to prove this. It says that question mark must be a term of this type, which I already know. And since we defined implies as a function, which takes a term of this part and converts it to a proof of term of Q, let us supply an argument to MP function. Now, Agda, when I compile it, if I had Agda, it would say question mark is a term of Q. Why? Because I already gave X to MP function. But X is a term of this type, and this type is constructed with an AND. By definition, Agda knows that. Let's see the definition of AND. It is P times Q, and times operation is given as a ordered pair. So I can split X into two parts, F, P. Why have I called this F and P? I have called it P because it's a function from P to Q, and P is a term of uppercase P. So again, question mark is a term of Q. I am looking for that. What do we have here? I have F, a function from P to Q, and I have a term of P. Let's just give P as an argument to P, FP, or we can write it as FP here, same thing. Then this automatically, by definition, is a term of Q because of the definition of F. Hence, when I compile it, Agda says it's okay. And that means that I have found the term of this proposition MP. Hence, our proof is done. So when I first saw this proof, not just the first time, but like over a month, I thought like it's just a magic. I couldn't believe it. Now I can't say I can understand it, but I know that it is because of definitions. We defined the conjunctions as expected. And also Curry-Howard isomorphism gives us the mechanism to understand why this proof works. So if we understand why this approach, the type checking approach works, we need to understand Curry-Howard isomorphism. Okay, I have 5 more minutes, so I can talk about the proof of De Morgan. It says that not P or Q holds true if and only if not P and not Q holds true. So we want to prove this. And classically, what we would do as students, we would just make it 2 parts from left to right and from right to left. And Agda automatically does it. Why? Because the definition of if and only if is given as a pair, ordered pair. So the De Morgan is a function, is a term of a term which is combined with an and. So I can use projection 1 over De Morgan and projection 2 over De Morgan. So I have here projection 1 De Morgan. It is the part where I want to assume this and show that part. De Morgan is a function, projection 1 De Morgan is a function, and I need to supply it as an argument. We are calling it F because it is not P or Q. And if you remember the definition of not, let's see here, is given as a function from P to falsity. So this, again, is a function. But what I want to get is something in the form of and, not P and not Q. These can also be splitted. So I use projection 1 and projection 2 to split it. And what I am looking is at the end, not P. Given F, I am looking for not P. But again, not P is a function. Let's write it. Not P is a function here, which takes P and reads falsity in logic. So let us give it as an argument P here. What I am looking is just false, because I have supplied P and I am looking for a false here. If I would write question mark here, Agda would say question mark is a term of is equal to false. Okay. How can I get false from here? Let's look at the definition of F. F is defined as a function from P or Q to false. So injection 1P, let's see here. Injection 1P takes P and returns P or Q because of the definition here. So if I give F injection 1P, then I automatically get my desired false here. And similarly, if I do it for the second part, projection 2 part here of the AND conjunction, I also get F. I have 2 more minutes. I want to talk about something else. Let's skip this part. Okay. As I said, type theory can be used as a foundation for mathematics, but it's specifically founded as a foundation for constructive mathematics. I will not talk about constructive mathematics today because of time constraints. And we can make type theory as a foundation for all classical mathematics. How can we do that? We can add axioms to our system. We can, for example, now we are in the environment Agda. There is a special syntax for that. And you can declare that I take this as an axiom, and from now on you can assume it. And in constructive mathematics, the law of excluded middle, as a statement that assumes P or not P for every proposition P, is rejected in constructive mathematics. But if you want to use it, you could just add it as an axiom to your system, and then prove your classical results, like Schroeder-Bernstein theorem or something else, which you cannot get away without law of excluded middle. So that is all I want to talk about for type theory. If you have questions, I can take them now.
Thank
you.
Thank you. Any question?